Let's look at one of the circuits with 555, and we will use now the mini notebook from Forrest Mims, and there's a pin description there. I will refer to the pins when we see a diagram like this one, and you can correlate those numbers next to the block to the function. Another tool that will help us to understand what we're building is a simulator. So falsat.com has one that we have been using, and if you click on circuits, you will find one that might help you. I'm doing this voiceover over a fast forward version of the circuit that we have in the Mims manual, and what I did was to select exactly the same values and add on the two potentiometers slider, and also I added the possibility of changing the resistance and capacitance of other components to see how do they work. But essentially you will see that I get these sliders, and when I move them, they move in the drawing, and the waveform output also changes. There is a frequency estimation, so you will see somewhere in the range of maybe hundreds for very low values, and in the range of 10, 20 kilohertz as a maximum, and this it happens to be coincident with the audio. So if we are smart about this, we are going to be able to see here the duty cycle, another term that you might want to research, and the frequency change when I move the sliders. So I expect to see that in the circuit and also to hear it. Another little tip that I thought that it was actually a source of information for all of us is that I have the habit of handwriting circuits I'm going to be fully understanding, and well, that's what I did with the timer. I put in there the main component, and I connect the power to the two pins, and I also label all the others, and one by one I'll try to get into details of how do they work. So there's a reset pin that right now I don't really use. The output is what we're going to be listening to, so I put a speaker. I will use another color so they don't overlap between the trigger and the threshold, where there's an RC circuit that is getting a midpoint, and then there's a control point that is a resistor divider. That in this case I put a potentiometer of 100 kilo. So now this is what we're going to be building, right? This is the thing. So I already assembled it once before filming the video. Let me get all the parts out. Let's start by saying, okay, there is a breadboard, and we have to read how to use it. We have to be aware of what to connect where. So the mid slot is not connected. The A, B, C, D, E are all connected. F, G, A, H, I, J are connected, but in between the half of the left and the half of the right are not connected. So the dual-in package has the advantage that I can insert that in there, and you can relate how I put the connections and I center the chip similar to the diagram I made. So I'm going to use a black color for the cables I use for ground. That is essential in my way of working. I understand that other people don't have that habit, but actually we peel off a little bit of the cable, we insert on the blue line or black line that you have on each of the power rails, and that way we know everything is connected there is ground. And I also make it very clear, because I use black color, that that's going to be the ground. So I'm not sure whether the first half of my breadboard and the second half are all connected, because different models of breadboards, they have different connections to the power rails. So I have one pin connected. I will connect here a little jumper cable, and I will use the multimeter to see if they're connected. I cannot see with my eyes. I cannot open the breadboard. So I will use the multimeter in the function that it has a symbol of sound, right? Leave it here. Let's see. I'm going to touch one of the terminals with this and this with the, yeah, okay. That's a good sign. See, what else do I have to connect? I connected already pin 1 to ground. I will need to connect also pin 6 to the capacitor that goes to ground. The capacitor needs to be 0.01 microfarads. That's the same as saying 10 nanofarads, right? 3,000 times. So if it's 10 nanofarads, it's 103. So 1 0 and then 3 zeros more to get to the picofarads. Before I continue, maybe I connect it there and but if I want to measure the capacitance, I rather use the multimeter. I use it on the F of farads, and we have a little bit of an issue. We need to take it out of the circuit to be able to measure it. The test leads by themselves, the cables, they already have capacitance. You can see the number is oscillating somewhere in the 10 picofarad. And I try not to touch with my fingers just because it will alter the measurement. And I see that it's 9.5 for nanofarads, very close to 10 nanofarads. So when I place it, I'm sure that I chose the right one. Okay, so far we have two connections. Let's mark them. Okay, I put the ground here. I put this capacitor, I put it to ground, and I connected a pin 2. So I have those three things that are connected. Now I have to be careful. I have to pay attention. What else do I have to connect, right? So pin 2 and pin 6 are connected between together. So I will use this wire wrap, and you already have one here. It's too short. You need to actually select which colors you use, how long the cables are. What I do normally is I cut the cables to the size, to the length I need, and I peel off the tip before cutting, so it's a little easier. You're holding a spool of the cable, and I don't cut completely. I peel off, right? So I use the wire clipper to a certain degree that it takes the plastic off but doesn't damage the copper inside. And then once that I peel both ends, I connect between 2 and 6. One technique that you can use is to go and fly over the IC. The 555 will not complain, but it's going to be also quite ugly and difficult to understand. So it's possible to connect them as you draw the circuit, going next to the integrator. So when we drew, we didn't draw lines on top of a block. When we make a circuit, we don't put wires on top of the ICs. Let's see how does that look. And yeah, we can make it tidier and look cleaner. But essentially what we're doing is we're trying to bring that thing that we drew on paper to the physical world, to the real world. And so it goes. I have now the breadboard with these very few, but these connections, and I have to understand them and mark on my diagram what I have already connected. And let's go on finding a 1 kilo ohm resistor. We already went over how to measure and how to read the color bands of resistors, but let's review. The test leads should be in common and ohm. Now we have this multimeter that is not auto scale, so we need to select something that is bigger than 1000. So you can start with the biggest, but I already know that is eyeballing that resistor is not 1 mega ohm. So I'm going to use my fingers because the resistance value is not that big, and I will see that it says 0.98 and then it's kilo, right? So it's going to be 1000 ohm. So I can check that I didn't affect the measurement with my fingers. So I put it on the paper and I touch it there. But for sure, it has to be stable. It cannot be that you are measuring and the multimeter is showing values that are jumping from 1 to 1,000. I heard that this was happening with some people. So something that you will be getting some practice is that when you insert something on the breadboard, you need to make the test leads straight so they are easy to push, and you have to be careful where you connect them. The first connections, I left the video original footage at real time, so you see I'm being careful, I'm checking where am I connecting, I'm double checking the circuit with a little bit of care and love and putting each connection. And then I'll go and verify that what I did was correct. With the other components, what I did was to go a little bit faster. You can read a little bit about potentiometers, but here I connected with resistance value, and I'm double checking that the middle point, it's the one that is variable in the circuit. So now I get into a mode where I'm doing several things one after the other. I'm looking at the component, I'm looking at the diagram, I'm verifying that what I have in my hand it's coincident with the drawing I have. I'm sometimes checking with a multimeter that what I think that is connected is actually connected, and I'm being careful with the cables. Every time I go on to connect them, I double confirm the position, and I'm trying to use different colors. For example, I use black for ground and yellow for VCC. So these visual aids, when the circuit gets more and more complex, are essential. Otherwise, you get completely confused. And the same with the drawing, right? You can eyeball having a connection of an LED when run resistor, but having 20 or 50 components is just not feasible if you are going to be guessing where are things connected. So now I have black color, yellow color, and others for signals. And I think that they add some value to leave the original footage there, so you also take a look at the steps I went through and where did I put the variable resistors. You can see that when there are no new components, there's no need to measure them. Then I go with a little bit of careful measurement when I get to put the batteries. I'll double confirm. I put in voltage. The tip I use 6 volts, and then I see one battery is like about 1.55. I connect the black terminal with ground, and now I'll go on and set the instrument in higher than 6 volts so it doesn't get to over limit, and I measure 4 of them. It's 6.2 volts. And for the battery case, I get the red terminal connected to the power rail, and you will see that here I have this little tip that is when you need to move 3 things together, you have only 2 hands, you can wrap a cable around your voltmeter, and that, for example, in my case is the ground terminal. I leave it fixed and use the other tip to look at the output that is going to be showing us the frequency. So I peel off the other part and I insert it into the ground. So we can hear 2 point something kilohertz, 11 kilohertz, we still hear it. When I go too high, 22 more, I can't. 2.2, I go up and down with these 2 knobs. So I'm using the multimeter in the hertz position, and what I'm seeing is kilohertz. So my ear is a good sensor, but when you get to like 36, it's just impossible to hear it. When it goes very low, let's see 60, 40, you hear something. When you go up, you realize there's a full spectrum among these tones. And that was it. I hope that it helped in some ways, especially the people that are now working for projects using the 555. All right, and don't forget to shoot me any questions when you are building your projects.
No, that's it.